Did you know the world's tallest building stands over 2,700 feet tall? That's taller than a half a mile. Today, we're diving into the fascinating world of tall buildings and urban density. I'm going to be talking with Phillip Quach, a structural engineer at RJC Engineers, about the role of tall buildings in addressing urban density and the importance of ensuring that design material standards reflect at-scale structural responses through research and full-scale testing. Today, I'm your co-host, Rachel Holland, and this is the Structural Engineering Channel. Before we get started, here's a quick word from our sponsor for this episode, PPI, a Kaplan company.
PPI provides expert prep courses and study resources designed to help you pass the FE and PE exams the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all the options available for FE and PE exam prep. Now let's dive into today's episode.
Welcome to the show, Phillip. Thanks so much for joining us. We would love to start out by having you tell us a little bit about yourself, your career journey, and what led you to become a structural engineer at RJC Engineers.
Okay, thanks, Rachel, and I really appreciate you guys having me. So, my name is Phil Quach. I'm a structural engineer currently working at RJC Engineers out of Toronto. It's a Canadian firm. We have some U.S. presence as well. And I worked in the AC industry as a structural consultant for just under a decade now, mostly interested in buildings kind of from a very young age. So sort of naturally fell into this. I've always been fascinated by the Toronto skyline. Even built a crane out of Lego once, which I think might have been my most proudest achievement in terms of Lego creation.
Nice.
So that was way back when I was a kid. I studied civil engineering at the University of Toronto. I graduated in 2013 with a Bachelor of Applied Science, and then I segued directly into a Master's of Applied Science at U of T again, just close to home, and their research and sort of academics were aligned with what I wanted to do. So I did some coursework and a research-based project focused on the shear response of large-scale reinforced concrete members, which we can talk about a bit later. And then through that experience, I witnessed a lot of research projects, even besides my own, that were kind of really large-scale experimental. So you could see it, you could feel it and touch it and see it in the labs. And they ended up directly, or some of which ended up directly translating to industry, practical use in the industry. And they weren't just kind of like the textbook academia and industry with a hard dividing line between and sort of no transition between. So that kind of really spoke volumes to me in seeing how that sort of relationship can happen between the two seemingly sort of separate entities. So that was exciting to see. And then they ended up being used in real projects kind of around the city and around the world. So coupled with that sort of fascination for tall and complex structures, it led me to RJC Engineers. As I mentioned before, it's definitely a leading structural firm at Canada, and being a good fit for my interests and passions, as well as they had those direct links with some of those kind of aforementioned U of T projects, which we can, again, discuss a bit later.
That's awesome. Yeah. So you mentioned like the being fascinated by the Toronto skyline, like just growing up in the area. How do you think that tall buildings play a role in addressing the need for the increased density in Toronto? And like, how do you think that will shape the way for future metropolises?
Yeah, so even growing up in Toronto, I could see such a ginormous kind of change in the skyline shapes and forms from child into sort of like high school, and then high school to university, and definitely university to industry now. It's been changing so fast you can kind of barely recognize the city you grow in. And this is kind of true for cities around the world, as they constantly expand to accommodate the population growth and kind of mass urbanization that's happening. And again, I'll speak purely through the lens of Toronto, as that's what I'm familiar with and kind of what I've grown and lived through. Like the RLB kind of crane index, I guess it's the metric of cranes around the world. I think at the end of 2023, and this is probably not up to date, I think things slowed down a bit, but we had 240 active cranes in Toronto that I saw, and that was ranked number one globally. I think the second city, I forget what it was, but it might have been 50 cranes, which is wild that, Toronto's seeing more than what I thought were some even more bustling metropolises in the
So
US.
wait, in 2023, you had 240 active cranes in Toronto. And then what was the 50 stat? The next busiest city?
Number 2 ranked was like 50 cranes. I forget the city. To be honest, I wish I had that. I had said it at like another presentation, but I forgot that the other city. So effectively, like a huge kind of leap from sort of, let's say, average development in metropolises around the world.
That's a huge difference.
Yeah, it was insane, and you kind of notice it with all the traffic in the city. But so it's kind of growing at an unparalleled pace, and vertical growth, I think, by means of tall buildings can really help support this urbanization amid kind of the density and transportation infrastructure constraints that we're kind of seeing, because it really maximizes the land use just by going up. And I think some stats just from CIBC, which is the Council on Tall Buildings and Urban Habitat, has shown that the number of tall buildings globally has really been increasing exponentially, really from the 2000s onwards. And given the affordability and maybe sustainability challenges that we face kind of in large cities like Toronto specifically, we have a lot of that. I'm not sure if the trend continues, but I do see tall buildings still having an important place, I think, in metropolises, as they do accommodate urban growth and address density issues quite efficiently, I would say.
So from the get-go, like, I know you talked about your Lego crane and everything, but like from the get-go, you wanted to work on tall buildings. Like that was your kind of like end goal.
I think just structures in general. I did have like a keen interest in tall buildings, just in Toronto, CN Tower, and then the downtown skyline. So maybe like a minor lean towards it. But even to this day, I'm still very much fascinated by structures of all shapes and sizes. Everywhere I travel, I'm always taking photos of just structures.
But in your day-to-day, you are mostly doing tall buildings, or are you exclusively doing tall buildings?
I would say mostly. Like we have across the company, at least, it's definitely a mixed sector and mixed use in terms of the projects. The group I'm in is more specialized in high-rise, but we definitely do some mid-rise as well. I don't even know the definition of mid-rise this day is like 30 stories, I think, which is kind of crazy. So I kind of wide variety, but more keen interest in the tall buildings for sure now that I'm in the industry.
Okay, and so like you just said, mid-rise is still considered like 30 stories. So what's typical stories for the projects that you're working on?
Nowadays, it's crazy that 60 is becoming normal. 60 stories for like residential, and then 50 story for commercial is like sort of I wouldn't say necessarily common. It's becoming the norm for massive developments in the city. Okay. So
interesting. Okay, so when it comes to the structural design of these buildings, like what are the key considerations and the challenges that you have to keep in mind in order to, obviously, safety, number one priority, right? And then like just the stability and the performance of the building too.
Yeah, some of the design considerations I say could be grouped into sort of 3 categories. First is building typology, then we have building materials, and lastly we have the structural system itself. And this is kind of general for all buildings, and I'll kind of narrow that in, I think, into high-rise and tall buildings. Speaking about the typology, this is really the occupancy and use of the building, kind of programmatic stacking, residential, commercial, retail, parking, and this dictates layouts, geometry, as well as loading requirements. The second thing is materials. So the most common ones, I think, are reinforced concrete and structural steel globally, but we're starting to see more kind of hybrid composite, timber, etc. And this is dependent on the typology as well as the practical engineering limits of the material. And then lastly, the structure, which will be the main focus, is like focusing on the gravity and lateral load resistance of the structure itself. And this is dependent on the aforementioned 2 items, the typology and the materials, as well as local building code requirements and market conditions. If we dive a bit into the structural systems, as I mentioned, we have the gravity, which is load resistance in the vertical direction. And the load path is typically like loads on the floor, spanning out to the vertical elements, columns and walls. And then taking these down to foundations. And then the lateral one, which we'll dive into more, is the load resistance in the horizontal direction. And this is the load path from lateral loading, wind, earthquake. We even have some less intuitive ones such as gravity-induced lateral loading, and those take the loads from the floors again, acting as diaphragms to the lateral force-resisting system down to the foundations. And then this is where we kind of get into like the challenges, I think, specific to tall buildings, is that specifically in Toronto, like lateral loading in the form of wind, it governs most of our buildings here, where we happen to have lower seismicity. This is not the case for, cities out west, a lot of cities in the US, where seismic can have a huge factor in the actual design of tall buildings as well as wind. And then these tall flexible structures experience lower seismic loads just by nature of their inherent softness, but then they become more sensitive to wind demands, which is why significant wind loads, just due to the parabolic nature of the wind profile, creates kind of complicated demands and challenges for our building, as well as having interaction with adjacent buildings. So on that note, I'll kind of segue into wind tunnel testing, which is something that's done kind of worldwide in order to properly assess the demands on tall buildings, as well as many other structures like bridges. But it effectively does scale testing at like roughly 1 to 300 to 1 to 500 scale of the real building. And they do this to probably quantify the actual loading in the context of its environment. So if you're in a dense cityscape, it's going to account for sort of that like upwind surface roughness. If you're in an open rural area, it'll account for like wind having no obstruction. So maybe seeing a higher loading in that regard. And this is done by companies such as RWDI, and they're able to sort of see more complex phenomena. One somewhat unintuitive one is called vortex-induced oscillation, which people may have heard of, but effectively it's vortices sort of shedding off the corner of buildings. So your building under wind moving in one direction ends up wanting to move side to side, and that could end up governing the building design, specifically for really tall and slender directions. So I always found that to be an interesting one and not something you'd normally think about. A couple other sort of aspects.
Just real quick, just a follow-up question on that, the wind tunnel testing. So for people that don't work in like, high-rise engineering scenarios, is that something that's always sort of like outsourced? Or is that ever like an analysis you would do in your company, or how does that work?
It's typically outsourced to a wind consultant, as they have the facilities to actually carry out the wind tunnel testing. The RWI has one in Guelph, which is like a massive building with multiple wind tunnels. The only company that I know, I think, that does it in-house on a smaller scale might be SOM in the US. I don't know if I recall, it's the Chicago office or the New York office, but
so this is like, they will literally build, like at the scale that you were talking about, they will literally build it and run the wind tunnel tests and give you the results. And then you take that for your design.
Correct. And that is like an alternative means to building code prescribed loads, at least in the National Building Code of Canada, or NBC, but I'm sure it is as well as in ASC. It's like you can use the building code wind loads, which tend to be conservative, and may not be conservative in cases of weird interaction effects, or you can use a wind tunnel analysis. And correct, like they build a model, we give them building properties just based off our structural analysis model. They incorporate that into their testing sort of jig, so it's sort of reflecting our structural building properties. And then they already have the city context sort of built for various metropolises. So they literally plug your model in the actual context. So then you can actually assess how the wind gets interrupted or funneled or accelerated through like the city leading up to your building. And then they put the wind in sort of like a 360-degree increments to see governing effects. And then they ultimately give you a database of loads that you run on your structural analysis side.
Okay. Do you guys choose to do that with most of your projects, or will you tend to go with the loads from the code? How do you how often?
I think for all tall buildings, we'll literally jump straight to wind tunnel. If they don't do it at the beginning, if we're trying to get early assessment, they do what they call a desktop study, which is based off of like previous projects and the wind consultant's experience to kind of give us an estimate of loads. They might do some CFD, which is like computational fluid dynamics, in lieu of doing the wind tunnel itself, because that takes a lot of time, money, and effort. So the final design for tall buildings will most definitely be based on a wind tunnel, as we don't like to rely on the building code loads for that.
Okay. And then what would you consider like the biggest obstacle that you've had to overcome in in high-rise building design?
Oof, there's a lot. I feel. In addition to sort of, like wind is usually the trickiest one, as in that's like our governing demand in the lateral sense. So that one's tricky depending on kind of geometry and the configuration of the tower. Some other ones I would say, I'm just not necessarily putting them in a hierarchy here, but axial shortening is something that comes into play a lot more with tall buildings. We have elastic shortening of the materials, and then if you have a reinforced concrete building, you have long-term shortening just due to creep and shrinkage, and everything shortens at different amounts just due to the stress levels. So we have to carry out more complex stage construction analysis to sort of understand these relative movements, so we can build the tower and different components taller, so that subject to like the full dead load, they kind of settle in to where they should be. So that facilitates cladding installation, floor finishes, and any like stiff interconnected elements. Like you want to make sure that we've sort of accounted for that. Pipe risers, that's another big one, because tall buildings settle a lot more than short buildings just by nature of the length, the height of the building. And this is something that's definitely tricky, and we ask some contractors to monitor this while during construction, so we kind of see if we're kind of close to target, and if we're off, what adjustments we need to do.
Interesting.
And the last thing I would say really for tall buildings is really, this kind of follows through to the other things, but this is what dictates the structural form, is the programmatic stacking. It's just we're getting so into like mixed use buildings, which is great for the people living in it. But when you're stacking different occupancies with different requirements for grid spacings, such as residential, commercial, and then ultimately we generally have parking below grade, it makes it really difficult to find kind of coincident lines of verticality. And then we end up with very convoluted structural load paths. And you can imagine transferring like 50 stories of gravity or lateral load resisting elements versus 10 stories. It makes for some kind of complicated gymnastics that are not ideal, I would say.
Yeah. What about, I mean, we've kind of been chatting about this, but like all the different design material standards, and like how important is it that you make sure that those are representative at the scale of represented at a scale when you're doing these taller, more complex buildings? And like, how does the research with like the wind tunnel testing and the full scale testing, how does this all come into achieving this?
That's a good question. So kind of like harking back to that point of like the skyscraper, whole growing metropolises, but like looking at the skyscraper in more focus, it's evolved quite significantly. I'm more familiar again with the Toronto ones, but I'm sure it's sort of a general trend across the world. Like for some time in the past, they got taller, but they remain fairly simple still and regular. And then in Toronto, at least up to the early 2000s, they started becoming way more intricate. And for those who are tuning into the video podcast, there might be some photos that are showing at least some projects under construction in Toronto. And you'll see just the geometry looks like wild almost. And they're very complex structural forms, and they're resulting from some site constraints and honestly the architectural programming, as we kind of alluded to earlier. Another photo which might be shown is just showing effectively this massive tower in LA in a high seismic zone, and its raft foundation for a 73-story hotel is 5.4 meters or 18 feet thick. It's massive. We didn't build like this maybe 50 years ago, maybe even 25 years ago. So I think with the building size and complexity increasing with ambitious architects and owner developers striving to meet the various needs of urbanization, we're really trying to do a lot with our structures, and we should be sort of getting the material standards reflecting the scale of the elements we're doing, and as well as the complexity of the elements we're doing, just to be sort of more in line with the structures we're building today. Yeah,
and it's definitely, I mean, this is true pretty much always, but we're just continuing to push the limits, right? So things are getting more and more complex. Phillip, can you elaborate on your Masters of Applied Science project at the University of Toronto on the shear response of large-scale reinforced concrete members, and talk a little bit about the significance for the engineering community?
Yes, of course. So this took a few years of my life, but it was a very fulfilling, despite stressful few years. But effectively, we conducted a large-scale experimental research program to assess the shear response of very thick reinforced concrete elements, sort of like what I was talking about before with that raft foundation out in LA. And we did this to validate the size effect in shear at these extreme depths that we're seeing more and more these days. They're becoming less uncommon. And effectively, the size effect is sort of, it postulates that the shear stress to cause failure of a reinforced concrete member actually decreases as the effective depth increases if you don't have any stirrups. It's counterintuitive. A simple way to put it is that the shear strength actually doesn't linearly scale up with the depth. And the reason for this is that deep members end up having larger crack spacings, and they end up with wider cracks. And then they get like reduced aggregate interlock, which is just sort of like friction along the rough surfaces of a crack. And that's the primary mechanism of shear resistance in the absence of having any transverse reinforcing. So these large members end up failing in shear once you get sliding on that critical diagonal crack, when the shear stresses actually exceed the aggregate interlock capacity. Sorry, that's a bit of a deep dive into it, but just to kind of frame why we did what we did. So under the supervision of Professor Michael Collins and Evan Bentz at the University of Toronto, we end up building and testing the world's deepest shear specimen, which is 20 meters long and 4 meters deep. And it was a deep slab strip, just meant to represent a slice taken out of something like a raft foundation, subject to one-way shear actions. To date, it's still the biggest one. UC Berkeley did a 3.5 meter test, I think back in 2021, which is also, they did a similar sort of style of testing to, again, assess the behavior. So that was good. I think that was done by Jack Mealy out there. So effectively, at the time, ECI 318, this was 2014, their shear provisions were based on empirical data derived from shallow member tests. So on average, I think the test specimens used to build that data set were on the order of 350 mils, so just over a foot. And just due to the size effect, this could be unconservative for deep members. And speaking of international codes, many of them actually don't account or don't properly account for the size effect. So we can end up with a range of predicted shear strength estimates by factors of up to 3 across the globe, depending on if you're designing with, the Australian standard, with the US, with Canada. So it's kind of, you can see there's a bit of a challenge for people to predict this. And flexural response, on the other hand, is quite simple. It's well understood. You can ask 100 people and you'll get probably answers within plus minus 5 to 10%. But shear in reinforced concrete is just quite complicated mechanically. So sort of to assess this understanding, we did hold a prediction contest during the experimental phase of the project to see how both industry and academia would fare in assessing the capacity, as well as like the full response of the specimen. We ended up having, I think, about 60 entries, coincidentally split 50% into academia, 50% into industry practicing engineers. And the kind of shocking thing was that half of the entries ended up having predictions of the failure load that were 1.5 times to 5.5 times the actual failure load, using various methods like finite element to nonlinear finite element to code-based equations. So again, it's
being that with that, you're saying like if they were to actually do that in practice, they would have been short. Like
yes, correct. Unsafe.
It wouldn't have worked for them.
Yes, okay. Unsafe. Yeah, okay. And that's sort of like the big kind of exclamation point to the whole project. Really was to sort of like, okay, this size effect is real. Prior to this test, we proved it at 2 meters. That was at U of T. We wanted to see if it was still true at 4 meters, at least if our equations were still correct up to that larger depth. That, again, is not uncommon these days. And effectively, the research did show that, and it extended the range of what we call the U of T size effect test series, which was just a bunch of shear tests spanning over decades that were looking at this particular effect, testing small to deep, varying different sort of elements in terms of the reinforced concrete section, like reinforcing ratios, et cetera, just to check this. And we found that the size effect is captured well by mechanical-based shear resistance models, like the one used in the Canadian standard, A23.3. And then just some quick numbers to kind of explain that. So we had a companion specimen. We always joke that I did like 1.5 tests because I really had the big guy. And then I had a super small one that was 300 millimeters, so just a foot compared to the 13 feet. That's a 4 meter deep specimen. And the 300 millimeter specimen failed at a shear stress of about 1 MPa. This is roughly 150 psi. That's very close to the ACI limit of 2 F prime C. So you can say the code is perfectly fine for members of quote unquote traditional depths. The deep member failed at a shear stress of only 0.41 MPa or 60 psi, which is about 0.7 root F prime C. So you can see if we're using 2 root F prime C for members this deep, we're definitely unconservative. So as effectively the big conclusion is, as member size increased by a factor of over 14, the shear stress at failure decreased by a factor of 3. And the crack widths near failure actually increased in terms of the actual width of the opening by almost a factor of 4. So the result of the project and my thesis ultimately enhanced the understanding of shear behavior in deep elements common today, and it had influence into updating the ACI 318 provision. So the 2019 version of the concrete code in America now does account for the size effect, albeit in a different way than the Canadian code, but at least it's now on the conservative side.
Okay. Excellent. That's like building up to that last sentence there. I was like, okay, and so is this in the code now? Like, do people know? Are we still like overestimating the capacities, or did we fix that?
Yeah.
So that's been incorporated then.
Yes. Yeah.
Excellent. Okay. What about one other question I wanted to ask you was about the viscous coupling dampers. Can you chat a little bit about those and how like you use them to supplement damping in structures?
Yes, I'll preface that by saying I'm not an expert in those devices. It was developed at U of T as a joint sort of industry and academic venture. So I did see the elements getting tested, and this is kind of one of the things I was really excited about because I'm seeing them in the lab, and then I'm seeing later in the news they're being put in the building. So that kind of sort of marriage of academic and industry were a big spark for me. So it was a company offshoot from U of T formed by an industry colleague of mine, Mike Montgomery, and then one of my professors at the time, Konstantin Christopoulos. So they created this company where they patented and came up with this device. And it's used mainly to replace coupling beams in coupled reinforced concrete core wall systems. There's other applications for them as well, but I'll focus on this. Just this is the more common one. And it just involves sort of multiple layers of viscoelastic material. This is made by 3M. Yes, the Scotch tape company. They also do really advanced material stuff. Bonded.
I think 3M does a little bit of everything.
Yeah, you're right. They're wild.
Yeah.
They're very prolific. And they put these layers of 3M tape 3M viscoelastic material sort of between steel plates so that you have sort of like this forking happening. And then what happens is when you put them in a sort of coupling beam configuration, as the building kind of racks, these things sort of like shear between each other. And it's that shearing deformation of the VE material that kind of creates this inherent damping. So it's leveraging this dominant flexural mode that's common in cantilever buildings, which is way more ideal than using damping that kind of relies on shear racking, kinematics, or anything else, such as like bracing or wall panels, stuff that relies on intrastory drift. And these VCDs, they ultimately optimize the structural performance under wind and earthquake loads at all amplitudes of vibration without sacrificing valuable architectural space. As we said, we just knock out our traditional reinforced concrete coupling beams and we put these VCDs in place. And then there's no extra volume or building massing required. And they end up providing supplemental damping in a distributed sense over the full height of the building or over the height of the building wherever we set the VCDs. And that's sort of dictated by what a company like Kinetica Dynamics would tell you, this is where we need it to provide the level of damping that you need.
So for you as like the design engineer for this tall building, that again is something that you'll work with that company to decide like how many do we need in a building? Where should we put them?
Correct.
Where are they going to be most
effective? It's almost like a triad of companies. It's like we have the wind tunnel consultant, which sort of tells us the level of damping we need for the tall building to control building motions, which is a key metric for sort of occupant comfort. And then with Kinetica, this damping company, they'll tell us, given the target damping, sort of how many we need over what height, where do we want it in the building. So yeah, it's a bit of a interesting sort of collaboration and interaction between companies to sort of dictate the final layout.
So again, question for people that don't work in high rises. Just as an example, how many of these would you use on a 60-story residential high-rise building?
Yeah, so a common case study advertised by RJC as well as Connecticut was a 60-story residential tower in Toronto. It's called YC Condos. And I believe that they used it over sort of like the middle 40 stories of it.
Okay.
And then only on certain coupling wall lines. So not everywhere there's a header beam, but just certain ones. And that's sort of part of the optimization process that Connecticut would undergo to tell you, like, this is where you need to put it over this height. So,
okay.
Yeah. And then
what about, go ahead. Sorry.
I was just like the last point of just, it provides distributed damping. So it compared to like more lumped or concentrated damping devices such as tuned mass dampers or tuned sloshing dampers, they take up little to no space, like I said, outside of the typical concrete volume required. And then they also don't need as much sort of displacement to mobilize the full amount of damping. So you end up saving a lot of valuable architectural space, usually at the top of buildings, because that's where you typically put something like a mass damper or a sloshing damper.
So, and you could use these would completely take the place of that. It's not like it's in combination with, it's a different method.
Correct. And it's not for every building. Like I can't really speak to when it's appropriate. There's like different sort of structural sort of dynamics and properties that play into when one is better than the other. But yes, it would be its own method. And then you wouldn't need something like a big mass at the top of your building, and you can sell those extra penthouse suites.
Yeah, I was going to say, and then you get an extra condo.
Yeah.
Okay. What are some of the highlights that you've encountered while working on different projects at RJC? And two projects in particular I wanted to ask you about were Park Road and CIBC Square. So I don't know if you can talk a little bit about those.
Yeah, sure. For sure. Park Road's more fresh in my mind. That's they both are, I guess, because they're under construction. I'll start off with Park Road, and that, again, is not quite high-rise by today's definitions. It's only 30 stories, but it's a very challenging one structurally and a unique one in terms of a residential tower in downtown Toronto. We're dealing with a very kind of complex form that has a reverse taper. So the building kind of comes down and then it tapers on one side and then comes down. So over 9 meters of the building, cantilevers from the roof all the way to the grade. And it does that to kind of open up some public park space below. I know that face is very telling. It's the same thing, I guess, engineers now. We're like, what do you want to do with the massing? But it ultimately causes this gravity-induced lateral demand that I was saying. It wants to tilt the building over under its own weight, like without the presence of wind, earthquake, like the building wants to tilt.
Just on its own. On
its own, exactly. So You get all these additional forces in like the stepping columns, any of the walls that jog, the slabs acting as diaphragms, requiring to kind of equilibrate those tilting forces and pull it into the core. And then the overall core itself has all these extra demands. So it definitely creates all these additional challenges that would not have been there if the building wasn't leaning. So I find that one to be quite interesting. And then taking a similar sort of note on cantilevering, CIBC Square, at least phase 2, is a massive office tower complex, 50-story commercial tower overhanging an active rail corridor. And again, I would preface this to say, like, I was involved in only certain aspects of the project. So, like, huge credit to the entire design team of many different engineers who collectively made it happen. But this building, instead of cantilevering on one side, the whole thing comes down and then it tapers on both sides. And then it comes down to effectively 1/3 of its overall breadth because of the rail adjacency. So this one cantilevers 12 meters. And then it has a very interesting structural scheme.
6 each side? Or 12 each side?
12 each side.
Okay.
Yeah. I don't know if you're familiar with, there's a project in Chicago by MKA, 150 Riverside North. It has the exact same structural sort of system where it has that overhang on both sides. And to be honest, we were only dictated by needing to cut the building back on the one side because of the rail, but because of balance and symmetry considerations, we did it on the other side as well. Otherwise, you would end up with the gravity lean. So it has that very interesting sloping column configuration, and maybe some photos that can be shown on the YouTube will help illustrate it better.
Definitely.
Yeah, but we have these massive, like 900 by 900 millimeters, so huge box sections that are almost with 5-inch thick steel plates carrying, I have the notes written down here, 75 meganewtons. So in US, that's almost 17,000 kips, or in human talk, 330 full garbage truck loads coming down on these sloping columns and then kicking in to the building. So just massive, massive forces. And the very fascinating sort of aspect of this is like when you have all these framed members with these huge forces, they all have to resolve at the node, these sort of concentric work points of where you need the forces to get introduced and resolved at these corners. And on this building, we used a lot of cast structural steel nodes, and one of which I don't have a photo of, it is 4 meters high and weighs 40 metric tons. So it's about 90,000 pounds. It's just massive. And when you start seeing these things on site, you're like, wow, the scale of it is kind of unreal
really
when you start standing beside the things.
Wow. Very cool. Yeah. I'm definitely want to see some pictures of those, and we want to share those with our listeners too.
Yeah. And then
those sound great.
Two more aspects I'll mention on the project that were, I guess, like a bit interesting compared to typical buildings. We had a top-down construction method used for part of the ground floor slab, and this was just required to make the tight site work. Like I was saying, on the one side, we're sandwiched by the rail corridor, and then on the other side, we have a neighboring building. So there was really no way to get construction logistics to happen without interrupting sort of major north-south arteries in downtown Toronto. So we did this top-down method where we drilled temporary piles, we installed the supportive excavation, the shoring, and then we built a staging slab, which then acted as a construction platform during construction so that you could put on excavators, mobile cranes, drive trucks over it while you dig underneath. And then you're digging essentially top down, and then as you go down, you build the structure, the substructure bottom up. So it ended up being a very interesting slab with temporary loading conditions, and we were just subject to so much construction equipment and logistics loading that were sort of atypical. We would put tower cranes on there, like I said, mobile cranes. There's one SPMT, which is a self-propelled modular transport. If anyone's ever seen those, it's those massive sort of vehicles with like an array of wheels used to carry big things, like a wind turbine blade, for example. But in our case, we used it to carry like a pedestrian bridge across this slab. And that weighed 360 tons, so 800,000 pounds. And we're having to deal with those loads as temporary loads, which is heavier than anything really the slab would see once it becomes its final permanent in-service condition. So that was interesting.
And I was going to say, like with that slab, it also did stay and serve a purpose, like for the life of the building, right? You don't tear it out.
Yes, correct. Sorry, I should have specified. It
Okay.
ended up being integrated with the full build out. So it was just like, let's say, half of the ground floor slab. And then when we came bottom up and we got to ground floor, we just built the rest of the slab and joined it in with couplers and keys. So yes,
Okay.
it wasn't scrapped.
Okay.
It serves a bit of a dual purpose.
Right.
And then just the last item, again, just always going back to the rail adjacency, we just had a crash wall, which is effectively, it's becoming more common nowadays as a lot of developers are looking to sort of build structures kind of right next to rails. Effectively, we required rail protection of the primary superstructure in the case of an extreme event such as a derailment and an impact crash. So we ended up designing this crash wall for a pretty large lateral load. It's 2,700 kilonewtons or about 600 kips, just to have this extra sort of capacity in case something bad happens with the train derailment. And this was sort of dictated by the ARIMA manual for railway engineering. So I will say that one referenced at the time, ACI 318.14. But we knew, knowing the Canadian code with shear provisions, we knew to bound it with the CSA provisions, just for the shear aspect that we were kind of talking about earlier.
So that's down at like basically the ground floor then, right?
Yeah, exactly. The building comes down and then it lands on ground floor.
You have all of that stuff from above coming down with that eccentricity, like the offsets. And then on top of that bottom wall that's already taking all of that, you designed it for the crash.
Yes. Yeah. There's a lot going on with this project, which is why I find it so fascinating, and there's kind of a lot of kudos for the whole design team and to put it together, because it's just so many different load effects are coming into this that otherwise would, not be there on a, say, more typical building.
Right. Wow. That's a complex design. So very cool. I'm looking forward to our readers or our listeners seeing the pictures of that one. So What about, okay, so another hot topic in the industry is always like sustainability, embodied carbon, all the different things with that. So curious how the industry is addressing the reduction of the embodied carbon in building structures, like what you work on. And have you seen a trend toward like this effort? Like, are you seeing anything in your field?
Yeah, it's a very good question. And the funny thing is, when I was young and I saw these crazy buildings, sort of like the ones I've kind of described, I was always so excited to work on them. And then having worked in the industry and seen kind of how complicated they get, you kind of take a step back, like, oh, I wish buildings were a little simpler. Like, again, you can do anything. Like, you can achieve a lot with engineering, given time and budget. But it's just, you're starting to notice that. And that wasn't even when I was young, I wasn't fully, admittedly thinking of sustainability. And then now it's like you're starting to kind of appreciate that, these things cost a lot of money, like structural gymnastics cost money. And I don't know as much about this, to be honest. I did speak with a couple of colleagues just to kind of understand a little bit more about what we're doing, what the industry is doing. But effectively, kind of carbon reductions are generally aligned with economic reductions because transfers cost a lot of money, balconies cost money. And what we're doing, I think across the industry, is just people are starting to do more robust measurements of material quantities just to assess the embodied carbon associated with different building typologies, materials, etc. We're trying to be a little bit more creative in our thinking and engineering to devise alternative solutions to transfers wherever possible. I don't know, an example is to like kind of step the column to avoid or to deviate a vertical load path instead of kind of coming down, transferring out. I mean, that has its own sort of complications as well, but that automation tools for structural analysis iterations to kind of help aid in decision making, and we can kind of do different versions of a structure and then see which one perhaps the least carbon intensive, that helps. And I think just owners and developers and architects with kind of a bit of push also from structural, and we're just kind of looking to minimize vertical kind of discontinuity and all that complex stuff that requires just so much structural material massing in terms of concrete transfers or heavy steel. Just it saves money. If we can encourage driving down structure uninterrupted straight down to foundations as much as possible, we'd avoid all these costly things from a material and sustainability standpoint. So I think there's sort of a pushback on that. And in addition, like our new version of our building code in Canada has become a lot more restrictive with things like that as well. So that could be another sort of side of pressure that's kind of getting us to revert back from some of these really structurally ambitious projects.
Right. Yeah. Interesting. So it's just like basically like a little bit of effort from all parties involved, and it just can hopefully go in that direction.
Exactly. Yeah. I think before it was like, oh, can you make this happen? And then as engineers go, yeah, of course, no problem. Like, yeah, we could. It's just maybe now with all those pressures, like we can, but doesn't mean we should. So I think that kind of reframing of the mindset will be good moving forward.
Yeah. Okay. So we like to ask our guests one final question that we always ask. And it is, what is your final piece of advice that you could share with maybe younger engineers or people who are interested in, maybe they don't currently work in like the tall building sector of our industry, and what would you suggest to them or give them as a piece of advice from you?
Okay, that's fair. The first one I would say, and again, this is probably just because I followed this route, is grad school is important. It's not always required, I think, in structural engineering, and not all job descriptions will note that. But I think it's quite important to kind of learn about the more advanced topics of structures, such as dynamics, advanced structural mechanics, and these things aren't really taught in the undergrad level. And those are important, particularly for larger, taller buildings, more complex forms. And research on that side, despite it being niche, it still can teach valuable skills in terms of problem solving. And if it involved experimental work, it can teach some practical skills as well. Because I learned how to tie rebar and sort of assemble stuff in the lab for my project, which I would not have really kind of thought about when I first thought about grad school back in my undergrad. So that's kind of one aspect. Another one, this one perhaps is more general to, I think, engineering as a whole, and not just kind of pigeonholed into tall buildings, but very much important, is just lifelong learning. Beyond what you learn, even from industry, I think it's important to actively seek and learn from, technical presentations, peer-reviewed technical papers, industry design guides. Like, I know I myself am always looking out for this. I'm like, I joke with at least my friends and other people that I don't even read anymore in terms of like the standard. I don't read books. Like all I do is like engineering, which is like the nerdiest thing ever. But it's just what I find interest in. So those are the things I think, and it helps you kind of, get ahead, like be on the kind of cutting edge of what the industry is doing, and it can help you on a project one day. Like just effectively don't let your knowledge or skill development stagnate in the heat of deadlines and kind of doing things that they've always been done. And then I think the last one is just kind of fundamentals, and again, general to engineering, not just for tall buildings, but I always tell even like younger engineers like to not get lost in the black box complexity of all our analysis and fancy design software and automation workflows. They can sometimes be wrong. And then like all this fancy, nonlinear finite element, 3D software, AI automation, I think we can easily lose a sense of, what's real. And also give a false sense of accuracy. So I always encourage people to kind of gut check findings and results against fundamental engineering equations as well as experience. And the latter comes with time. Should always be sort of within the correct order of magnitude of things. Like you should know the max moment you can get in a span is, W squared on 8. I don't know, 60-story building should have like a fundamental period of vibration of like roughly 6 seconds under like wind properties. Otherwise, if you're getting something like off, then you should definitely, it warrants an investigation. And I'll kind of finish off with a quote. I think that my professor, Michael Collins, had always said, this is one of his principles of engineering. And it seems paradoxical, but it's to find the answer, you must know the answer. And that's kind of you kind of need experience to practice engineering, and that comes with time, but you'll get to a point where like when you find something that, a software spits out, or maybe you're looking at a set of drawings in it and it looks wrong, then you don't know that it looks wrong until you've done it so many times that you kind of know roughly what the answer should be. And that's when you just start, raising the flags or checking it or, diving a bit deeper. So
I definitely remember that was something that one of my first bosses really like hit home a lot. Like, look at that. Does that seem right? And I'm like, I don't know. I'm new.
At the time, right? You're like, I don't know. Without that kind of guess sense.
Yeah. So, okay. So that's great. So be a lifelong learner. Consider grad school if you want to work on some more complex projects, and then also do a gut check and obviously get better at that with experience, because
I'd say
it's hard to do that right at the beginning.
Yep.
Awesome. That's excellent advice. Thank you so much, Phil, for joining us. And it was so great to get to talk to you and hear a little bit about your experiences.
Thank you so much. Thanks. I really appreciate it, Rachel. Again, appreciate you guys having me on the show.
Awesome. I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and/or questions. To leave them, please visit thestructuralengineeringchannel.com. There, you'll find a summary of the key points discussed in today's episode, as well as the links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.